The psychology of similarity. The question, what makes things seem alike or seem different, is one so fundamental to psychology that very few psychologists have been naive enough to ask it. F. Atneve, 1950. What does it really mean for two things and two ideas to be similar to each other? In many ways, this seems like a trivial question. We know that two dogs can be similar to each other. They are both dogs, they both bark, they have tails, drool, etc. But would they be less similar if only one of them had a tail, or if one was large and the other small? And beyond that, how do we make a distinction in terms of how each of these factors affects perceived similarity? Are they similar because they share important features, or are they similar just by virtue of being dogs? In other words, what seems simple to describe at first is actually fairly complex. We need to be able to determine if things are similar or not so that we can compare new things to existing mental representations and make decisions about them. In this way, similarity is one of the building blocks of cognition and underlies much of the psychology of thinking. Objectives. In this chapter, we will answer the following questions and work to understand the following topics. What is similarity? How do we define it? And how do we understand it? How and why is similarity involved in the thinking process? Why is it important to study similarity before considering other topics related to thinking? Understand how similarity can be measured, assessed, and described empirically. Understand major psychological theories of similarity, how they work, and what some of their limitations are. How can an understanding of similarity be applied to learning new material? What is similarity? For most of us, similarity is a construct that is easy to recognize but often difficult to describe, but I want to start this chapter with an attempt to define and describe similarity. Things can be said to be similar if they share perceptual features, if they share common attributes, or if they evoke the same behavioral response. For example, we would probably behave the same way towards two apples. We can enjoy eating them because they have the same shape, the same smell, and they evoke the same response. These two apples would be similar. We would probably put them in the same category as a result of this similarity. Similarity seems to be a domain general construct. This means that it operates according to the same principles, whether or not the objects or ideas being compared are visual, auditory, lexical, directly perceived, or recalled from memory. If I can arrive at some calculation of similarity by comparing two photos of dogs, it might be pretty much the same as if I saw the dogs in person or was asked to recall an image from memory. This does not mean that similarity judgments are unaffected by context, but it does mean that similarity as a computation is carried out in the same way regardless of context. Of course, as soon as we decide that similarity is domain general and seems to be universal, we also have to account for the incredible flexibility and fluidity that exists in how people understand and rate similarity. For example, if I hold a Canadian penny and an American penny, I would rate them to be quite similar. Even though they are currencies from two different countries, the composition is similar, their shape is similar, their role within the monetary system is similar. Set aside the fact that the Canadian penny has been discontinued and the American penny has not yet been. Suppose I am then handed a Canadian nickel. Does this change my understanding of the similarity between the American and Canadian penny? Are the Canadian penny and the Canadian nickel now more similar to each other? Or are there two kinds of similarity at play? In other words, my perception of surface similarity allows me to rate the two pennies as being similar, but there is also a deeper, more conceptual similarity that allows me to rate the two Canadian coins as being similar. Consider extending the example even further by imagining that I am handed a Japanese yen coin. Functionally, it serves the same role as the penny. Conceptually, it seems an outlier as the other coins are North American in nature. Does it change the similarity among the three North American coins? There is no set answer to these questions. I bring them up to illustrate that similarity is flexible. There is more than one kind of similarity. We can appreciate similarity between and among objects at different levels. Similarity in thinking. Similarity plays a role in many core cognitive processes and is an important aspect of many higher-order thoughts as well. Below is an examination of several of these, but the list is not exhaustive. Object recognition. First, let us consider the process of visually recognizing objects in the world. Quite simply, we are adept at being able to see an object, an apple for example, and near instantaneously, and from a variety of viewpoints, recognize the object, name it, access categorical information, grasp it appropriately, etc. This process of object recognition is often assumed to require an assessment of the similarity between the incoming perceptual representation and the mental representations that have been stored in memory. Whether we assume that the pattern matching process is done via stored exemplars, stored images, a stored list of non-accidental properties, there is generally a role for the mental computation of similarity. Objects are recognized, in part at least, as a function of their similarity to stored patterns of known and previously seen objects. An understanding of similarity is thus crucial for an understanding of the object recognition process. Of course, not all formal theories of similarity specify an explicit role for object recognition. This is merely an acknowledgement that similarity plays a role in a general sense. Memory retrieval. As another example, consider the process of memory retrieval, discussed in more detail in Chapter 3. Semantic memory, memory for facts, is assumed to be organized conceptually. That is, if you are trying to remember something like a name or a place, the chances are that you will also remember similar things as well. In order to retrieve the right memory, a retrieval queue must contact the most similar representations in memory. This idea underlies many influential models of theories of memory organization and structure. As such, similarity between related memory traces and similarity between a queue and the to-be-remembered item is going to play a role in memory retrieval. Memory retrieval errors are also a function of similarity. We often make errors by retrieving the wrong but very similar memory. Many early cognitive theories of semantic memory demonstrate the importance of similarity with the basic idea of spreading activation. Essentially, spreading activation occurs when a single target concept is activated, and that activation spreads to other related concepts. The degree of spread is influenced by similarity and may also be taken as an index of similarity. This is typically measured in terms of reaction time in a lexical decision task. A lexical decision task is a task in which letter strings that are either words or non-words are presented visually to a subject. The subject is required to respond quickly with a judgment of whether the string is a word or not. Since the error rates are usually very low, the dependent variable is usually the subject's reaction time to respond. If a subject is presented with a target word, such as fork, the subject should be faster to correctly identify the word knife than to correctly identify an unrelated word like truck. The fork and the knife belong to the same category, perform similar roles, are used in similar contexts, and are often made of similar material, so we expect the activation to spread from one concept to the next. The faster reaction time is an explicit indication of this similarity. Other models of memory, such as the instance-based model known as Minerva 2, for example, are built upon the notion that similarity between memory traces is a major component of memory retrieval. In this particular model, memory retrieval functions as a result of the similarity between a probe and many retrieved memory traces. In this model, the probe can be thought of as a cue or a prompt, requiring the system to recall a memory. This probe contacts as many stored exemplars as it can, but exemplars that are more similar to the probe are retrieved more quickly. A probe that is able to contact many similar exemplars very quickly corresponds to memories that are retrieved easily. A probe that contacts few exemplars or takes longer to contact exemplars corresponds to memories that are less easily retrieved. In other words, there seems to be an important role for similarity in memory encoding and retrieval. To the extent that memory influences higher-order thinking, a point that is covered in Chapter 3, it is clear that similarity will influence the thinking process. Problem solving. Similarity also seems to play a role in problem solving. As an example, consider the process of a student learning to solve elementary algebra equations. At first, the process of keeping the equation balanced might be complicated, and the student needs to keep straight the rules for how to isolate the variable that she is solving. In other words, it is a complex problem to solve and places a significant demand on cognitive resources. Furthermore, suppose that the student is going to be learning several kinds of algebra problems: linear equations with one variable, linear equations with two variables, quadratic equations, etc. Initially, solving each kind takes effort, and keeping each kind of problem straight also takes effort. As the student acquires more skills, she begins to recognize the patterns and rules for each problem type. If a new problem is similar to the one that has been solved in the past, then she can use the same set of strategies to solve this new problem. In other words, problems that are similar are solved similarly. A problem solver can use this assessment, similarity, to assist in solving problems. Empirical research has supported the idea that similarity plays an important role in problem solving. For example, influential research by Newell and Simon, 1972, describes problem solving as a search through a defined problem space. The problem space is simply the arrangement of the current state, the goal, the obstacles to reaching that goal, and the operators that allow one to reach the goal. Solving a problem, then, can be thought of as a process of moving through the problem space from the initial state towards the goal state. How would one keep track of the progress? One possibility is that problem space navigation is a process of tracking the increased similarity between the current state and the goal state. In other words, the problem solver knows what the goal state or solution state is supposed to look like and can compare the current state to that representation in order to determine which action or behavior to choose next. The topic of problem solving is covered more extensively in Chapter 10, where the role of similarity will be made clearer, but it is worth introducing the idea now in the context of similarity as a general psychological construct. One of the best examples of the important role that similarity plays in problem solving, and one that we will discuss later in the chapter on problem solving, concerns the role of similarity and expertise in physics. In an influential paper, Ch et al. 1981 asked physics PhD students, experts, and undergraduate students, novices, to sort 24 physics problems into groups and then explain the reasons for their groupings. Novices generally sorted the problems on the basis of surface feature similarity. That is, they grouped problems according to the literal physics terms mentioned in the problem and the physical configuration described in the problem. Experts, on the other hand, sorted their problems on the basis of deep feature similarity that were related to the major physics principles governing the solution of each problem. This suggests that experts accessed existing schemata and they used their knowledge of physics to create a solution-oriented sorting. Since the problems were sorted according to these categories, it also suggests that these categories would likely be accessed when deciding how to solve a problem. That is, experts are likely to rely on similarity among problems to help them solve the problems quickly and efficiently. Inductive reasoning. Inductive reasoning typically involves generalizing and making predictions about the future based on past events. For example, you can infer or predict that an apple will have seeds based in part on your prior experience of apples. Specifically, if every apple you have ever eaten has contained seeds, you can infer that the apple in your hand also contained seeds, even before you take a bite. This is a strong argument because apples are very similar as a group. If you were to make a prediction about the tartness of the apple or its suitability for pies, you might be slightly less certain, because not all apples are similar on these dimensions. The point is that similarity is a powerful driving force behind many inferences. In fact, a complete theory of inductive reasoning is built on the notion that similarity is a primary determiner of inductive strength. The similarity coverage model of Oscherson and colleagues assumes that inductions and inferences are based on an understanding of the similarity among the items or concepts being considered in a given argument. Although I will devote an entire chapter to this topic, Chapter 6, it is worth describing here in preliminary detail. Simply put, inductive reasoning is a mental process by which we make predictions about future outcomes based on our knowledge of something. This is predicated in part on an assumption that the future will resemble the past. Consider this example. I cut into a pumpkin and I find a mess of seeds and stringy pumpkin fibers. Every time I cut into a pumpkin, I find this. When I see a squash that greatly resembles the pumpkins that I remember cutting, for example, another pumpkin, I can predict what I will find even before I cut into it. I will find a mess of seeds and stringy pumpkin fibers. Now imagine that I cut into a squash that looks a lot less like a pumpkin, a Hubbard squash, for example. Having never seen one, I might still expect to find fibers and seeds, but I might be less confident because the Hubbard and the pumpkin are less similar to each other than the pumpkin and the other pumpkins are to each other. In short, the similarity between the two items helps to determine the strength of the inductive inference. The inference is strong in the case of pumpkins to pumpkins because they are very similar. The inference is less strong in the case of pumpkins to Hubbards because they are not as similar. The assessment of similarity. As the sections above suggest, similarity plays a major role in many of the core cognitive processes that are part of what we call thinking. For most of these examples, it is assumed that a person makes a quick and automatic judgment of similarity between concepts, or among category members, or between memories. The similarity judgment has to be fast and automatic in order for memory retrieval to be fast and automatic. But just what is a similarity judgment? What is the character of judged similarity? The problem is that within many of these processes and theories, similarity is an elusive construct. We still do not have a strong idea of what it actually means for two items to be similar, but subjective similarity and a person's judgment of similarity can be measured. In the following section, I want to review the most common ways to measure and assess similarity. Rating task. Perhaps the most straightforward way to measure similarity is simply to ask people how similar two objects are to each other. This would typically be done in a similarity rating task. Subjects would see a series of pairs of objects, concepts, words, etc. On each trial, the subject would indicate on a scale of 1 to 7 how similar these objects are to each other. Usually, 1 corresponds to a label of not similar at all, and 7 corresponds to a label of extremely similar or exactly the same. For example, a Granny Smith apple and a Gala apple might be given a rating of 6. A Granny Smith apple and a plum might be given a rating of 4. It is worth noting that the rating will be influenced by the choice of other items. Granny Smith and Gala apples are similar in the context of fruits, but if all of the comparators are other apple varieties, then the rating would be expected to decrease. The information provided in a task like this is subjective and variable, but in many ways that is the point. Over many presentations, and with many different subjects, the same two items should generally receive high ratings if subjects agree that, all things considered, the two objects are similar to each other. Correspondingly, if subjects generally agree that two objects are relatively less similar to each other, then the two objects should receive low ratings. Of course, on its own, a ratings task like this is only moderately informative. Later we will discuss more sophisticated models that rely on the information gathered from similarity rating tasks to gather more in-depth insights into the structure of objects in psychological similarity space. One of the benefits of this approach is that it is simple and straightforward. Ratings differ between people, and even within a single person's judgment, but on average, there should be some agreement about the relative similarity among objects. However, one of the downsides is that an approach like this does not really tell you how the judgment was made. It offers no additional insight into the underlying conceptual structure. Furthermore, a strict ratings approach will be sensitive to contextual factors, but may not explain them very well. In other words, think back to the example used earlier with the coins from different countries. In one context, the pennies may seem similar to each other, but in another context, they may not seem very similar to each other. By just asking for a similarity rating, you only collect information about two things in isolation. Another downside with this approach is that many people find it challenging to assign a single number to a similarity judgment, or they tend to assign only 2 or 3 numbers rather than all 7. Although the rating task is designed to be subjective, it can be difficult from the point of view of participants to really know the difference between a similarity rating of 3 and 4. Forced choice task. Another way to measure similarity is with a forced choice task. It is called a forced choice task because the subject is required to choose an option. A common variant involves a single target stimulus and two or more alternatives. The subject is instructed to choose which one of the two possible alternatives is the best match for the target stimulus. The match is subjective, and the subject could be given instructions to choose the stimulus that is most similar to, most like, or goes best with the target. One advantage of a forced choice task is that it is sensitive to context. In fact, it depends on context in order to force the person to make a decision. Consider again the task of rating similarity among different kinds of fruit. Suppose you present someone with a target that is a red apple, and the possible matches are a green apple and a red plum. There are many ways to make the choice, by color, size, the kind of fruit, and maybe you can even make the case that each stimulus is similar to the red apple target in its own way. But the point is that you have to make a choice, and the idea is that by presenting subjects with many trials, the researcher can, as above with the rating task, gain some insight into a subject's subjective sense of similarity. A task like this might be better suited to the more problematic example of the coins from different countries. If presented with a Canadian penny, an American penny, and a Canadian nickel and asked to choose which two are most similar, it is not the overall rating of similarity that matters. In this case, the subject is forced to choose the best possible match, even if he or she does not find it to be especially similar. In this case, all that matters is that two things are more alike than the other two things. Sorting task. A third way to understand the similarity between things or among things is to ask research participants to sort objects or pictures of objects into groups on the basis of similarity. A task like this is generally carried out with objects or with cards depicting objects. Participants are usually given instructions to sort the objects into as many groups as necessary based on which things go best together. For example, if I were given many different coins of different denominations and local currency, I might choose to sort them on the basis of country of origin, or I might choose to sort them into size groups, or I might opt for a combination of both, depending on how many coins need to be sorted. Unlike the rating task, there is no number assigned to the similarity. Just like the forced choice task, the sorting task takes advantage of contextual effects on similarity judgments. If a researcher is interested in knowing how objects are grouped together on the basis of similarity, this sorting task is ideal and is commonly used. One downside to a sorting task is that participants are usually not given strict instructions, which means the analysis of sorting data can be challenging. The researcher must infer from the groups what similarity metric the participant was using. Summary: ratings tasks, forced choice tasks, and sorting tasks are useful because they allow the researcher to collect quantitative data about a series or set of stimuli. All three tasks provide some insight into the similarity structure of a concept or the perceived similarity between or among objects. However, those ratings alone don't explain everything about the structure of mental representations. In order to understand how perceived similarity among items affects the structure and the nature of mental representations, we need to address and discuss several theoretical approaches to similarity. Theoretical approaches to similarity. We have established that similarity is a crucial construct for many basic tasks, and that the measurement of similarity often involves making explicit decisions about what is usually a fast, implicit process. But so far, the actual construct is somewhat elusive. Even the measurements described above presume to be getting at an underlying similarity. The question is, how does similarity actually work? How is it calculated, represented, and used by the mind? A variety of theories have been developed over the past few decades that explain similarity, and many of them have in common the notion that similarity is essentially the result of feature or attribute comparison. The more features or attributes that two concepts or objects have in common, the more similar these two things are. The geometric model. For example, one fundamental approach to similarity is commonly known as the geometric approach. It is often instantiated as a mathematical framework known as multidimensional scaling, MDS. The general assumption is that the similarity between two things is a function of the psychological distance between them, and that psychological distance is analogous to physical distance. Another way of putting this is that two things that are very much alike and are described as similar should be close to each other in psychological space. Analogously, two things that are not alike should be distant from each other in psychological space. In other words, psychological space operates like physical space. Two objects that occupy nearly the same coordinates in psychological space are similar. Because space is necessarily defined as the distance between things, after all, outer space is just what exists between other things. Psychological space is nearly always referred to in terms of distance. Similarity is defined as a small distance in psychological space. That is, the most similar that two things can be is zero distance. There is no distance between them. The formula for psychological distance, as it can be calculated from a comparison of two objects, is given in equation 2.1. In this equation, the d, a function of I, j, means the psychological distance between two things, I and j, and the assumption is that we are comparing them along a set of relevant dimensions, n. Each dimensional comparison is represented by the absolute value of the difference between them. Crucially, the equation includes an exponent that allows for the comparisons to be made along what is known as city block space and Euclidean space.